Chapter 3, Section 2, Graphing Linear Equations. We're going to talk about solutions of equations, graphing linear equations, and applications. It talks about, like the first section we talked about kind of how we get information from graphs, and really what we need to do at first is focus again what a solution means. A solution is the values that replace the variables that make the equation true, if it's a solution to an equation. Later on, same thing with inequalities, if the values make the inequality true. So that's what they start out with here. They say, well, let's look at this example. It says determine whether each of the following pairs is a solution to 4b minus 3a equals 22. And then they give us this thing that they've been defining as an ordered pair. And we set some rules around that because we need to know where the 2 goes and where the 7 goes and so on with this pair of numbers. And what we're trying to find out, if I put this pair of numbers in here following the rules, will it make both sides of this equation equal? Now, they substitute in here 2 for A and 7 for B, because unless they tell us otherwise, we go alphabetical order with our variables. So the first number will be the lowest in alphabetical order, in this case A. So they put a 2 in for A, from that ordered pair 2, 7, and they put 7 in for B. So we end up with this expression here of 4 times 7 minus 3 times 2. And we get 28 minus 6, use order of operations, and we get 22 equals 22. Well, that is true. So this ordered pair 2, 7 made this equation true. So it is a solution. That ordered pair is a solution. In the other ordered pair where we had 1, 6, when I put those in, I find out that it doesn't make it equal. I end up with 21 on one side and 22 on the other. So they're not equal. So this other ordered pair is not a solution. The ordered pair 1, 6 is not a solution. Remember, they're in order for a reason, right? If we didn't have some rules on the order, we wouldn't know where to put those values. Now, example 2, they show us something which is one of the standard, not a standard form, but it's one of the forms that we use in linear equations a lot. It's called the slope-intercept form, and we'll cover more about that later. And they say, well, show that the pairs, these ordered pairs 3, 7, ordered pair 0, 1, and ordered pair negative 3, negative 5 are solutions to this equation y equals 2x plus 1. Then graph those points to find out another pair that is a solution. So what they do is, well, let's put the ordered pairs into this equation and find out if it really is a solution, which means it'll make something true and true and true. And that's what they did with each one of these, just like a check, right? When you check to see if you truly have a solution. So these 3 ordered pairs are solutions to this equation. And the next thing they asked us to do was to graph that. Well, I plot these points, and remember, in ordered pairs, the other rule around ordered pairs, other than this alphabetical order, which it is true in x, y, right? X comes before y in the alphabet. But also, if we don't have any definition of, the order of our variables, the first number in an ordered pair is horizontal change, the change that happens left to right. The second number in the ordered pair is vertical change. So in this case, for this point 3, 7, it means that I'd start at the origin, which is 0, 0. I'd move 3 to the right, and then I would go up 7. Positive 3 means go to the right 3. Positive 7 means I go up in a positive direction to 7. And then at that location I plot a point. So it's kind of like a map. I start at this same point all the time, and if this was a grid of a city, I could say you go to street 3, so I move over 3 blocks, and then you go up to Avenue 7 or something like that, right? So it would be an address or a location that's described with this ordered pair. Well, that's the first one, and then I need to plot the second one. And I end up with, now in this case, 0, 1. The horizontal change is 0. In other words, I have no movement left or right, so I start at 0. I don't go either up, left, or right. I stay right there. And then I have a vertical movement of a positive 1. I go up. It's also good to note, and we'll talk about this a few times later too, is what is true about every ordered pair on this y-axis, it's called. Well, this one's 0, 1. If I went to this point right here, kind of where the index finger is, right, I would end up with 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. Hey, every point on the y-axis, the x-coordinate is 0, because there's no horizontal movement to stay on this y-axis. And we'll talk about what that means, because we'll do some graphing and some analysis of linear equations when we're talking about something called intercepts, where it crosses the axis. In this case, a y-intercept would cross at the y-axis. Well, the third point is negative 5, negative 3. So I start at 0, I go negative 5, which means I go left to the 5. And is that correct? Right? Got to be careful about order. I said it wrong and then started doing it. But the order is negative 3, negative 5. So I start at 0, I go to the left negative 3, which is a negative direction, right? Going to the left. And then I go down 5 to get to negative 5. So this ordered pair, negative 3, negative 5, is plotted right here. Now if you take a straight edge, and it doesn't necessarily have to be a ruler, probably what's available to everybody now is a cell phone. On the edge of that cell phone it's probably straight, and I could put that cell phone and put it so I have all these points kind of line up, and I can create a line and draw a line through that. And what they're illustrating is that there are an infinity of solutions to this equation here. These are only 3 of those solutions. If I did this correctly, and this truly is a linear equation, then all 3 of these points that are solutions that I tested end up being true. They're solutions, need to sit on that line. But there's other ones, right? I could take any point on here. In fact, I could keep doing this. I put value in for x and see what y happens, right? In fact, this is kind of like something I'll get into later too, called a function. It's like a machine where I have this little thing that says up that if I put a value in this little machine, like 2 in this case that they're doing right here for this ordered pair 2, 5, when I want to find that, what they're saying is it looks like if I go 2 to the right, I end up over here, it looks like at 5. So 2 up, 5, 2 to the right, 5 up, I end up right here. It looks like that's right on that line. But I better test that and put 2 in for x and put 5 in for y and see if it ends up being a solution. And in this case it is. But I could do that basically just with the equation. What they want you to do, and really what this section's about, is not the best way to graph lines. We're going to get some better ways to graph lines. But it's important to get this picture of what's going on with these equations. That this is a way to draw a picture of my solutions is all the points on this line end up making this true. And if you can draw a picture of any application, that's what you do. Well, now we've created a grid system with axes and a way to manipulate our locations on there with these ordered pairs. So I have basically a canvas that I can illustrate or draw pictures of these linear equations. And that's the point here. Really, this section is not, it's about really understanding what kind of view of the solutions there are and what those solutions are. Because graphing really isn't the best way. You know, if I would have said 1/2 for x, it'd be pretty hard to figure out exactly what the value for y would be here. Those kinds of things. But if I put 1/2 in for x, I'm going to get a solid value out of for y, or an ordered pair, and it'll be a solution. So here in this box they talk about solution equations in two variables. The solutions of equations in two variables are ordered pairs. The ordered pairs replace the variables of the equation in alphabetical order unless otherwise stated, right? To graph the equation is to make a drawing that represents the solutions, to get a visual of it. So you got a picture of what's going on. Every solution of an equation is represented by a point on the graph, or location on that graph. Every point on the graph of the equation represents a solution. In other words, it goes both ways. So that's what we're going to do. We're going to graph linear equations. And we're going to do it kind of similar to what we just experimented with, and really trying to get a picture of what solutions are, and literally get a picture, right? So equations like y equals 2x plus 1 we were kind of working with, or we could have something like this: 4b minus 3a equals 22, were the examples we looked at, and they both end up being linear. In other words, the solutions draw a line, and the graph, we talked about what graphs are. So they have a pattern that happens when they're in this, and we're going to talk about form a little bit. It's going to get more important as we go on with this chapter. This form where y equals some number, in this they put an m there for that, and we'll talk about what m means in a while, times x plus some number b. And what they're setting up is a slope-intercept form, where the m is your slope, and we'll talk about which is a fraction, and this indicates where this equation will cross the y-axis. And when you think about what are all the ordered pairs on the y-axis, the x value is 0, and so on. And this is called standard form, where we have some number times x plus some number times y equals some number. And why they name these, or start kind of saying, hey, look at these things, they seem to have a form to them, right? Well, there's going to be some strategies that we apply based on what kind of form we're seeing. And that's what they're going to talk about here. To graph a linear equation is one, select the value of one coordinate and calculating the responding value for the other coordinate. In other words, if I just take a guess and put a number in for x, I end up with an equation with one variable, and I can solve that. And when I solve that, I can figure out what the other part of that ordered pair needs to be. Now, I don't always have to start with putting the x value in. I could put a y value in and see what the x would have to be for that ordered pair to be a solution to the equation. So they repeat to find the second ordered pair and third ordered pair and so on. But basically and then you plot those ordered pairs, draw a straight line passing through their points, and the line represents all solutions to the equation. Now, what I see with students a lot of times is you learn this method, which you say, hey, I get this, and then you start graphing this way all the time. This is not the best way to graph. It's not the most efficient way, and we're going to work on more other ways. What this is really about is trying to get really solid in your mind what a solution is, and what is a pattern, and what happens when we have things or equations that look like this. So they say, well, we're going to graph y equals negative 3x plus 1. And then they say, well, what if x was 2? If I put 2 in for x, I'd end up with y equals negative 3 times 2 plus 1, which is negative 6 plus 1. And I end up with y equal to 5. In other words, I have a relationship between this x value and then this y equals negative 5. So I get an x of 2, a y of negative 5. That is an ordered pair. Horizontal change is the first number, vertical change is the second number. If I put 0 in for x, which I like multiplying by zeros, so I end up with y equals negative 3 times 0 plus 1, In other words, 0 plus 1, which is 1. So I get the ordered pair when I put x in, a 0 in for x. My y has to be a 1 to make this true. In other words, this is a solution. And then if I put negative 1 in here, they show the math. I end up with negative 1, and the y would have to be 4 for that to be the solution. Now I have 3 ordered pairs, and I can plot those on my grid, and you'll see on your My Math Labs and stuff like that, it'll show little lines when you have the graphing tool and do that, and you're actually looking for the line graphing tool. When you pull these points, you'll end up pulling the line along to line up with these points. And all I really need to draw a line is 2 points. Why do they always go with a third? Well, if I made a math error on, let's say I just took these 2 points, and I thought this one was 0, 2, not 0, 1. Well, this would be a solution, negative 1, 4 would be a solution, then I had this other one that was a mistake. If I drew that line, the only solution that's on that line is this position. Well, if I take 2 points, I can make that error. And then if I had that other point here and then I graph this point, and I go, whoa, I can't put a straight line through this point and this point and this point. I know I got a math error, I can redo my work. So it's really a checkpoint that all 3 of these have to line up. So they show methods. This is a very good way to do this with a table, stuff like that. You'll have a T table, sometimes they talk about, where you don't have to put a box around it. I just put a T, put X and Y. I know that they're going to really talking about ordered pairs, and then I plot that and I can graph. So example 4, we have y equals 2x minus 3. They do the same thing. And when I have multiplication involved, I almost always will put in a 0. And we'll end up with y equals 0 minus 3, or negative 3. So here's an ordered pair that's a solution to this equation, which is plotted right here. Then if I put 1 in, I end up with negative 1 for y. That's this point. 4 in, I get 5. Those 3 points should be in a line, and then I basically highlight that pattern with a straight edge, like the edge of your cell phone, and make sure you draw these little arrows on the end, because it really goes off for infinity. I could put anything in here for x or even y, right, and solve it. I could put 2 million in for x, and I'll get a y value out, but that plot point will not be on this graph. It's going to be way off, someplace else, because this does go on for infinity. Now these are kind of in something called the slope-intercept form. This is standard form. And what they really were pointing out is when you get something in standard form, I should look for the points that are on the axes. In fact, it's used so much they actually name it later on. They call them intercepts. But if I put 0 in for, well, let's do it the way they do it here. If I put 0 in for y, I end up with 4x plus 0 equals 12. I end up with this new equation, right, with one variable. So I have to solve this. So I have to take the reciprocal of 4 times both sides. So I end up with 1 times x, which is x, and that's why I used reciprocals, right? 12 times 1/4 is 3, and I would hope that that gets to be pretty easy to do. And I get really worried when I see students are still using calculators with that simple fraction multiplication, because 12 is 3 times 4 times 1 over 4. I could write that as 4 over 4 times 3. So I get 3, right? It's like pre-simplifying your fractions. So we end up with this solution. If I put 3 in, or if I have 3 for y, x is 0. Okay? And the second value is, I get used to doing the x first, kind of made me pause. Well, the other way I could do this, I could put 0 in for x, and I end up with this new equation of 2y equals 12. Take 1/2 times both sides. A lot of you will be able to guess and check here. What 2 times what gives you 12? You're going to know it's 6, right? So I end up with the ordered pair 0, 6. Well, there's 2 of them. And then I put another one in. I put 2 in for y, and I end up with a new equation. I need to solve 2 steps here, right? I have to add a -4 to both sides. I get 4x equals 8. Take 1/4 times both sides, and I get 2. But I do want to point out that when I have zeros in here for ordered pairs, again, if the x value is 0, I know that point will be on the y-axis, because every point on the y-axis, right along where this hand is showing, the x-coordinate is 0. Well, if you look at the x-axis, what's the same about every ordered pair here, too? Well, I got 0, 0, I have 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, and so on, -3, 0. Every point on the x-axis, the y-coordinate of my ordered pair is 0. And that's good to notice, because we're going to use that intersection of where the lines intersect the axes, and we're going to have some special names for those. Now, example 6 is where the variables are on both sides. We can solve for one of the variables, and that's what they do first. And they create basically like a function machine. They solve for y by multiplying 1/3 times both sides. And you end up with this new equation, y equals 2/3 x. Now you could put values in for x, right? And figure out what the y would have to be. If I put 0 in for x, I end up with 3y equals 0. In other words, y has to be 0. So 0, 0 is a solution. They don't even attempt that one. But they tend to want to solve things for y, and there's some really useful reasons for doing that later on. Well, with this model, like we've done similarly, we can put in an x value and see what comes out of this function machine. It's like a machine. I put in a number and it takes 2/3 times it and kicks out a value. In this case, if I put 3 in there, it kicks out a y value of 2. If I put a -3 in there, I end up with a -2, and I put 6 in here. Do you think there's some reasons why they pick these numbers to input in here? You know, obviously some big ones really is that they're all multiples of the numerator, or the denominator, excuse me. So when I pre-simplify these fractions, you know, I get a whole number. And I'm not going to put 5 here, because then I'm going to end up with 10/3, which is a solution. X is 5 and y is 10/3. You know, that's a little harder to plot, isn't it? It's nice when I can get out these integers for coordinates, because my grid is usually organized in a grid of 1 unit at a time, so I end up with something that's easier to deal with these. Well, again, that fraction stuff, if you remember how to multiply fractions, you will see opportunities to do just what the book is doing here. I'm not going to stick 1 in for x and then find out what y is. Excuse me. In other words, I get y is 2/3, because that would be hard to plot on this grid. I'd like to take the opportunity, even though I have fractions, to come out with non-fraction results. Example 7 here, we got x plus 5y equals -10. And the same thing, they say solve for y. You know, we've done a lot of solution stuff with equations, so let's use it. So what the first step they do is add a -x to both sides, which is the addition principle, as long as I do the same thing to both sides. Here's something too, you know, I haven't talked about very much, but remember when we had fraction bars, I said, well, you know, what's on top of the fraction in the numerator and what's on the bottom of the fraction in the denominator? It's really like there's grouping symbols around them. So you can multiply times that, but if you have an addition or something, you have to multiply times everything. Well, equal signs are like that too. This x plus 5y, it's like it's grouped together here on this side of the equal sign. Now I can break that grouping because of the associative property, which is addition, right? So I'd like to stay in addition here, so I add a negative x to both sides. That changes x into 0, the identity of addition. Kind of running through chapter 1 stuff with the correct wording, right? And I end up with this new equivalent equations. The solutions to this equation and the solutions to this equation are the same. That's what equivalent equation means. And then I need to get this 5y to be y. Well, I need to take this multiplication of 5 and change it into a multiplication of 1. So I use the reciprocal of 5. And this is really important here. When I have students who are really locked into always wanting to do division, they get into trouble here and are not used to using multiplication of reciprocals. It will cause you some problems in chapter 3. So if you haven't figured that out yet, this is a good time to really focus in here. Why are they doing it this way? And I'm going to give you a lot of reasons why they do it this way. Well, 1/5 times 5 is 1. 1 times y is y. So I get this y. I'm trying to solve for y. And then this is a grouping symbol. I get 1/5 times this entire side. So I get 1/5 parentheses, times parentheses negative x minus 10 parentheses. Now I need to distribute. And 1/5 times a negative x is a negative 1/5 x. 1/5 times a negative 10 is a negative 2. And they say caution. We need to use this distributive law. We've got to remember that if I multiply, I need to multiply by the entire side. Okay. Well, in this case, they start throwing ordered pairs into this thing. Now, you could easily use this standard form and pull out some ordered pairs pretty easily and do that, or you can use this slope-intercept form. You might as well practice it now because we're going to use this form a lot. But either way, we'd end up with the same ordered pairs. If I put 5 in for x, I'm going to have a negative 3 for y. If I put 0 in for x, I'm going to have a negative 2 for y. And then I would put in here, if I put 0 in for y, I'd end up with negative 10 for x. But they put in with negative 1 or negative 5 and negative 1. You end up with these 3 ordered pairs. Well, with 3 ordered pairs, I can safely draw a line representing all the solutions to this original equation. Okay. Now, applications. Well, now we're dealing with 2 variables, and we're talking about an infinity of solutions. So we're going to end up with, a lot of times, a conditional or basically a relationship kind of solution to my problems too. Example 8 is about fuel cost. It says the amount of fuel that an engine burns while idling depends on the size of the engine. The table at the left lists the annual costs of idling for 5 minutes per day in various engine sizes. These costs are based on gasoline price of $3.75 per gallon. The annual idling cost can be approximated by this equation, where C is cost and A is the amount of, or the engine size, excuse me. I probably would have used E, but they talk about the engine size is A and this is C. And they probably didn't use E because then this table would have to be reversed because we would think the first value, right? Alphabetical order. This is going to be my first value in the ordered pair second. Well, with that, this deal, if I try this, it means every one of these are solutions to that equation. And we could graph that. Well, we could graph the equation by selecting those values, right? You could actually graph it by selecting actual values that they gave you. And probably why don't they use that? I mean, I'd maybe use 2, right? 34, and they do. Why not 3.5? Well, that's harder to graph on a grid. Figure out exactly where that halfway point between the lines are and so on. So they're going to take values in here where I can get integer values for my ordered pair. And that's why they do it that way. So I basically put in a value for A. What does my Y have to be to make that a solution? And then they talk about that. Now if I graph this line, this graph is probably more an illustration of how the costs go for engine size just by looking at this line. If my engine size, which is this horizontal change, when I go from 2 liters to 7 liters, the annual cost goes up from somewhere around here, which is $35, all the way up to above $120. We're talking about, there's a lot of variables in this situation. When you're idling, it may depend on the temperature that's outside. All that kind of stuff will affect the amount of gas you're burning too. So it isn't like we have to have this, but this graph, basically, this line probably illustrates this better than listing this data. I can say if you look at this and pull out the information, you get a pretty good picture of engine size related to cost of idling. And that's exactly, now this caution here too is that equation. When I use the equation, I put values in for X and find out what Y needs to be, or A and C in this case. That is a better way to go than trying to pull solutions off of a graph. That's what this caution is about. Because graphs are really just supposed to give a general image. Because we don't have fractional values listed in these little links right here in between these grid lines. So we don't come out with real exact values by looking at a graph. And that's what that caution is about. In other words, the graph is not a great way to pull solutions. A graph is a great way to illustrate patterns and stuff like that. It is better to go back and actually put values into the equation, like right here, and do this and get values. So if somebody came to me and said, I want to know how much would it cost me if I had a 5-liter engine? Well, then you would put 5 in for A and then figure out what C would be. Now you'd get a fractional C, but that would be a better way to pull out a solution to that question. And that's what this caution is about. Now there are a lot of different kinds of graphs that use ordered pairs, with 2 variables. Here's some example pictures of things that happen if you have like y equals x to the 2 power. You end up with this curved object that's called a parabola. This is y equals the absolute value of x. So if I had y equals x, I'd have 1, 1, 2, 2, 3, 3, right? These ordered pairs. And then I'd have -1, -1, right? Well, when I take absolute value, if I take the x value is -1, the absolute value of -x is a +1. So I get this ordered pair up here. It creates a V instead of a line. And then when I have cubed or to the 3 power, I end up with this curved pattern. Now it can vary a lot depending on the pieces that are in this equation, on where it crosses the y-axis, how wide is the curve as it goes through there, and so on. And we can go through some strategies to try to get a pretty good representation of the solutions. And that's it for section 2. There's a lot of terminology. There's a lot of things there that we're not going to use a lot of, other than it's very key piece to understanding linear equations. And then we'll go on to some better methods to actually make the graphs and show ordered pair solutions.